Hey guys, I hope you're ready to do some really fun algebra today because today we're talking about implicit differentiation. And so with implicit differentiation, we are able to do things like this. We are able to find the tangent line of an equation or graph that isn't necessarily a function. So I have this graph, this is the unit circle, and I'm really interested in finding the equation of the tangent line at the point 6, point 0.8. So just, I really could do it for any point that lies on the circle. But the problem with this is that we're used to finding derivatives only whenever it's solved for y, when it's a function. So we're going to talk today about some methods that will help us do that. So I've written down, it seems like quite a lot. I hope you can see it clearly. Um, Kind of some notes. So I'm just going to walk through this. I'm going to have to write them all down. If you want, you can pause the video, write them all down, and then hit play again. All right, so let's talk about them. So if you want to differentiate implicitly, you're really going to take the derivative, but the big issue comes when you try to take the derivative of y. So when we differentiate, and most of the time, unless our independent variable is something like t or z, we're differentiating with respect to x. Um, so, but that means that when we differentiate a y, we have to differentiate y with respect to x. And so we have to include this little dy dx or a y prime every time we differentiate. So we end up doing something like this. If we try to differentiate y prime, then we're going to use the power rule, differentiate just like we know how, but then at the end we have to include this dy dx, or if you prefer, include a y prime. I prefer the dy dx. I think that the y's and the y primes can sometimes you can get confused which one is which. Now I gave you this helpful hint because this is one of the biggest mistakes I see students make is differentiating and using the product rule. So if you see a term that looks like this, x times y, um, these are two different functions multiplied together. You can think of it that way. So you have to use the product rule. So you would end up, taking the derivative of your first term, which would just be x prime times y, plus your first term times the derivative of the second, so that would be x times the derivative of y. And then you just simplify. All right, so once you have gotten everything differentiated, then in order to actually find what the derivative is, you have to solve for dy dx, which in terms of the algebra is sometimes the most difficult part. So the last thing I said is you want to take every term with the dy dx or y prime and move it to one side of the equal. And then your remaining terms are going to go on the other side. And then what you can do is you can factor out that dy dx, and then whatever you have left over, that's going to be in those parentheses, you can just divide both sides by that. So now that you've kind of got an idea, it doesn't really make sense till you do it. So let's try. Let's try to find the equation of this tangent line. So in order to do that, we have to find dy dx so we can find the slope. So I'm going to differentiate this thing. So I'm just going to take the derivative of both sides. Make sure that a lot of times you'll see these where they're equal to a constant. Make sure you realize that the derivative of a constant is 0, and you don't leave that as 1, because obviously it'll make your answer wrong. All right, so we're going to differentiate this, and we get 2x, that's just normal, plus the derivative of y squared is 2y, times dy dx is equal to 0. So now I want to move everything with a dy dx to one side. So I'm actually just going to leave this here, and then I'm going to move this thing over here. So I get 2y dy dx is equal to negative 2x. Now I want to divide both sides by 2y. And I end up with dy dx is equal to negative x over y. So now I'm part of the way there. So now I want to find my slope and plug everything in. So if I want the slope when x is 0.6 and y is 0.8, then I am just going to plug those in. Negative 0.6 divided by 0.8 and I get negative 3/4. Since these were given to me in decimals, I'm going to leave this as negative 0.75. Right, so now I know my slope, right? This is m. And now I just want to plug everything into my point slope formula. So this is going to be y minus zero point 0.8 is equal to negative 0.75 times x minus zero point 0.6. And you have your equation. Now the algebra on that one was pretty easy. Let's see if we can look at a different function. I'm going to flip back through. So I really like this graph. You can look at some really neat graphs when you're talking about this stuff because they don't have to be functions, so they can do all sorts of things and squiggle along. Um, but here's one that we want to find the slope of the tangent line at 1, 1. So I'm going to start just by differentiating each side. So I can find dy dx. And so I get 4y cubed. I'm differentiating y, so I have to put dy dx plus, and now this is xy, so I gave you this example earlier. You have to use the product rule. So this is going to be the derivative of x, which is 1, times y, which is just y, plus the derivative of y, which is dy dx, times x. I'm running out of room, so I'm going to put it down here. And this is equal to, and then do the derivative of the right-hand side. So this one's all x's, so it's just 3x squared minus 1. Okay, so now I want to, these parentheses I really don't need because it's just all added. So now I want to take everything with a dy dx, and it's going to go on one side, and then everything without it is going to go on the other. So let me see what I have. This has a dy dx. This has a dy, oh, no, sorry. This has a dy dx, right? And then I have, so I'm actually just going to leave these two things on the left-hand side, and then I'm going to take this, and I'm going to move it over to the right-hand side. So I end up with 4y cubed dy dx plus x dy dx is equal to 3x squared minus y minus 1. I put the y in the middle. I kind of like it that way. So now my next step is to factor the dy dx out of both terms. Okay, and now I can divide both sides by this term, and it'll cancel out, and I'll end up with dy dx, it'll cancel out on the left side, sorry, is equal to 3x squared minus y minus 1, and divided by 4y cubed plus x. And there we go. Now I want to find the equation of my tangent line at 1, 1. So I'm just going to go through and I'm going to plug in 1 for x and 1 for y. So I get that dy dx is equal to 3 times 1 minus 1 divided by 4 times 1 plus 1. And so I get 1/5. And now I can just write my equation of my tangent line using the point slope formula. So y minus y1, which is 1, is equal to 1/5 times x minus x1, and x1 is also 1. And here is my equation. Not so bad, huh? And the algebra, I mean, once you get to the end, the algebra looks pretty messy. But honestly, you're doing the same process over and over again. So I find this is less challenging than some other complicated derivatives because when you simplify, you don't have to determine the best method for simplification. You do the same thing every time. Move everything with a dy dx to one side, everything without it to the other, factor it out, divide by what's left over. So I did find one where the algebra was pretty challenging, and I'm going to tell you that you can simplify however you want. You can put it in whatever form you'd like. If you are if you're studying towards the AP Calculus test, then they're really not particular about how you simplify. So I didn't simplify this all the way out, but I wanted to talk to you about how it would look once you get your answer. All right, so we want to find dy dx. So I'm going to start by taking the derivative of both sides. Now I'm going to have to use two separate quotient rules for this piece on the left. So I'm going to take the derivative of the top, which is dy dx, times the bottom, which is x, minus the derivative of the bottom, which is 1, times the top. So I get dy dx minus y, and then I'm going to divide this whole thing by x squared. And that's the derivative of this first piece. All right, so now let's do the derivative of the second piece. So I've got the derivative of the top, which is 1, times the bottom. So that's just going to be 1 times y, which is y, minus the derivative of the bottom, which is dy dx, times the top. So I'll write this as x dy dx. And all divided by the denominator squared. So it's going to be y squared is equal to, and then this is just going to be 2, because the derivative of 2 times a variable is just a constant. But I'm differentiating y, so I'm putting my dy dx. Okay, so this is really fun, right? So there's several ways you could do this. You know, I just thought of a much easier way than what I started with. I'm going to multiply everything by x squared, y squared. I initially split fractions, and so I made, this one fraction and that one fraction and so forth. But I think if I just multiply everything by x squared, y squared, that'll make my life a lot easier. That'll get rid of all my denominators. Don't forget to switch both sides. Now, although you've done all your differentiation, you cannot stop here. You have to solve for dy dx, as complicated as it seems. So I gotta adjust my window a little bit. Okay, so when I multiply this through, the x squareds are going to cancel. So when I do this x squared and that x squared are going to cancel. And so I end up with y squared times my numerator. And so if I do y squared times my numerator, it becomes dy dx x y squared minus y cubed. So now we're going to distribute this to this piece, and now the y squareds are going to cancel. So I'm going to be left with x squared y minus x cubed dy dx. And this whole thing is equal to 2x squared y squared dy dx. All right, now it's not so bad. Now it looks kind of like the other problem. So same deal. So move all the stuff with dy dx to one side, all the constants to another. I generally always put my dy dx on the left, but I just read left to right. So let's do this. So everything with the dy dx is going to stay on this side. This piece is going to get moved over to this side. And then these two are the two pieces without the dy dx. They get moved to that side. That looks like a pretty messy diagram. Oops. Okay, so let's see what happens. So we get dy dx x y squared minus x cubed dy dx. And then I'm bringing this thing over, so this becomes negative 2x squared y, 2x squared y squared. Couldn't read my own handwriting. Dy dx. And then it's going to be equal to, this is a negative y cubed, so that'll become positive, and then positive x squared y, so that'll become negative. All right, so now we factor out the dy dx. So this becomes dy dx x y squared minus x cubed plus 2x squared y squared. Oh, that's nice. Is equal to 2y, no, sorry. Is equal to y cubed minus x squared y. So now we can divide. So we get that dy dx is equal to y cubed minus x squared y all over, excuse me, xy squared minus x cubed minus 2x squared y squared. Lovely. And there we go. We didn't have to. We didn't want to find the slope or anything. We just wanted to find the derivative, and it actually turned out really nice. All right. So now what I want to do is something a little different. I want you guys to try a problem all on your own. So pause the video, work the problem out, and then start the video back up, and then I'll show you the answer. All right. You guys ready for the answer? It's a lot of writing. Now let's see if you made any mistakes. It's really tricky, so you got to pay attention. Okay, so the very first thing I did is I used the product rule to differentiate the left-hand side. So check and make sure you use the product rule correctly. So it's going to be the derivative of x, which is 1, times the second, plus the first times the derivative of the second. And then since we're differentiating e to the y, the derivative of that is just e to the y, but you have to multiply it by dy dx because you're differentiating the y. All right, so now let's check out the right-hand side. Remember that you have to use the product rule on this one. All right, so let's try this. So we are going to take, and I've grouped this. I put the 2x together as one term and the y as the other. So the derivative of 2x is just 2 times the second, which is y, plus the first, which is 2x, times the derivative of the second. The derivative of y is just dy dx. And then the third, the y cubed, I use the power rule. So I bring down the 3y squared. I'm differentiating y, so don't forget the dy dx. So now we have to flip-flop, right? Everything with the dy dx goes on one side, and everything else goes on the other. So let's see what I moved over. So this piece right here stayed. So that's what went first because it was the positive one. And then what did I move over? So this piece got moved over and it became negative. Right, this piece got moved over and it became negative. All right, let's clean up. And let's talk about the right-hand side. So I found everything without a dy dx, which was this e to the y. I moved that across the equal, so it became negative. And then the 2y stayed where it was. And so I'm now down to my third line, this line right here. So I've explained all that. Now you guys should have factored out this dy dx, right? And then we put that in front, and then we wrote down what was left over. And this was x e to the y minus 2x minus 3y squared. And then it's all equal to 2y minus e to the y. Now we divide both sides by this piece right here. I hope y'all did that. So we could solve for dy dx. And then we get this down here. So once again, not a lot of, it's tedious, but honestly, you don't have, a lot of thought doesn't have to go into it because when you're simplifying, you're using the same method of simplification every time. Everything with the dy dx to one side, everything else to the other, factor out the dy dx, divide. All right, I hope that I have helped you guys learn how to do implicit differentiation and have fun. You can do lots of practice problems. You can practice the odd problems in your book. Look up the solutions. It's always helpful. And I will see y'all soon.